Hey, today I want to introduce you to a really revolutionary idea that shook the world of physics around 1900. And it's the idea of quantization and the birth of quantum. So in the early 1900s, physicists pretty much thought they had things figured out as far as Newtonian physics, the idea of being able to predict the outcome of certain mechanical experiments. They had this concept of a mechanical universe where if you could measure things like an object's mass and current speed and enough about its direction, then you could predict what the outcome was going to be of any mechanical experiment, a collision, or just predicting where a planet might be 2 years from now. But there were still two problems that baffled physicists. One was the idea of black body radiation, which led to this theorized ultraviolet catastrophe. Now, we're not going to spend much time on this. If you want to look into it, there's lots of information on the internet, and you can look at kind of the basic idea of the black body radiation to a lot of detail about it. We are not going to spend much time in this course talking about that. We are going to spend our time talking about something called the photoelectric effect. In the end, both of these problems, the solutions, really led to the same conclusion, that energy is quantized. Now, you're going to hear the word quantum or quantization quite a bit as you move forward in physics. Just to be clear, the idea itself, in essence, isn't that complicated. It basically says that things come in multiples of a basic amount. A good example might be currency. If you think about Canadian currency right now, the lowest denomination that we have is a nickel or 5 cents. So we would say that any amount of cash that you carry with you has to be a multiple of a nickel. Everyone walking around with money in their pocket has a certain amount of money that is divisible by 5 cents. So we would say that our money is quantized and the quantum of our money is a nickel or 5 cents. So from that perspective, quantization seems pretty straightforward, but if the idea of quantization and quantum physics doesn't have you scratching your head by the end, then you're not thinking hard enough about it. So let's talk a little bit about one of the real nails in the coffin of the mechanical universe, this idea that everything can be studied with the laws of Newton, and that is this phenomenon we call the photoelectric effect. The basic phenomenon, which we're going to understand in a little more detail, is this observation made by physicists that when light strikes a metal surface, it may emit electrons. Now, these electrons will be referred to as photoelectrons, but to be clear, photoelectrons have the same features as an electron. The only reason people refer to them as a photoelectron is because they are a result of the photoelectric effect. Now, here's the idea. In this picture here, let's focus our attention on this picture here to start with. The idea was this, or what was observed was, if you had a piece of metal that was charged up, and the best way to observe it, and as is shown in this animation here, the best way to see this is to use an electroscope. So when it's charged, an electroscope has a leaf that is kind of displaced from its normal resting position. So we have here three different electroscopes, and they're each charged up. You can imagine each of these being charged negatively, so that on the surface of these plates here, as well as down here, there's a bunch of negatives. And the photoelectric effect phenomenon was observed and demonstrated here when you shine light, and there's really three experiments being shown here. When you shine light onto this charged electroscope or any charged piece of metal, you have the opportunity and the potential that the electrons might be emitted. Now, in the most classic experiment, the metal was zinc, and when you shone red laser light at the zinc plate, nothing happened. So you have no, what I'm going to call PE, no photoelectric effect in this case. If you begin to use maybe a form of ultraviolet light, you might have the photoelectric effect starting here, but only if you get it high enough. So in this case, still no photoelectric effect. But when you get to this final one, when you get ultraviolet light, and that ultraviolet light is higher frequency than this one, then you get the photoelectric effect. And what that is these electrons will start jumping off this surface, and as a result, these leaves fall, and you get evidence that you have discharged this electroscope through the photoelectric effect. A more simple diagram of the photoelectric effect is shown here, where you have a surface, and on the surface are electrons. When red light hits the surface, maybe we don't get the photoelectric effect like we see here. So no photoelectric effect with red. If you change from red to green, go to a higher frequency, you might start to get the photoelectric effect as they demonstrated here. But the photoelectric effect really comes down to this. Certain frequencies and wavelengths of electromagnetic radiation will eject electrons from a metal surface. So if red doesn't do it, maybe green does. If green doesn't do it, you try blue. If blue doesn't do it, maybe you go all the way up to ultraviolet. That is the photoelectric effect. In a nutshell, the emission of electrons from a metal surface that is caused by a certain frequency of light or electromagnetic radiation. Now you might say, what's the big deal? Well, it was a big deal, and the big deal is this, that there is a discrepancy between classical theory and what we've talked about in terms of a wave model of light and what was really observed. So let's consider, if we're thinking about the classical physics model or the wave theory of light or electromagnetic radiation, think about this. If I asked you, I want to increase the energy of light, you would say the energy of light is determined by the intensity or the brightness of a light bulb. So in the photoelectric effect, if I asked you, or if we started with a situation where light was shining on a surface and we were getting no photoelectric effect, how could we get it? A classical physicist would say, make larger waves. If you make larger waves, in other words, brighter or more intense light, if a dim light bulb didn't work, a brighter light bulb would, because brighter means bigger waves mean more energy. Unfortunately, or to put it better, fortunately, people observed something quite different. Energy seemed to be related to the frequency or wavelength. Think back. It wasn't by changing the amplitude of the light that we got the photoelectric effect. We changed from red to green to blue to maybe ultraviolet light. So we changed, somehow the energy is related to frequency or wavelength, not the brightness or the amplitude of the light. The second discrepancy was this. In the photoelectric effect, electrons should be emitted by any color or wavelength or frequency of electromagnetic radiation. We just might have to wait longer. In other words, if you picture a wave carrying energy, then each crest and trough carries with it a little bit of energy. If you hit an electron with that energy, so we shine light towards an electron, then it makes sense if this is a wave of energy, the energy accumulates. So at first, the first wave hits the electron, shakes it a little bit, starts it vibrating. Then the next wave comes along, shakes it a little more. Then the next wave comes along, shakes it a little more. The more you hit this electron, or the more time you allow the wave to hit the electron, the more waves that hit it, the more energy it gets. And you would think it would accumulate, and eventually this thing would have enough energy to jump off the metal surface, creating the photoelectric effect. But that doesn't work. Turns out that if you are below a certain frequency, you get no photoelectric effect. And when you're above this certain frequency, there was a photoelectric effect, and it's instantaneous. It takes no time, which again is contrary to what classical theory would say. Classical theory would say if energy is traveling as a wave, there's a little bit of energy on each part of the wave, and you have to wait for a while for that energy to accumulate. But the photoelectric effect said, no, that's not what's happening. As soon as the light turns on, we get the emission of these photoelectrons. So these three discrepancies, these three situations in which classical theory kind of falls down or is not confirmed by the actual observation is, number one, a failure of classical physics, but not the end of the story. It is the potential, the possibility for new theory. And that's exciting. And that is where we stepped off the precipice and we left classical, what they call Newtonian physics, which is great. When you study lab carts and you look at collisions and you want to know how far a car is going to go in 30 seconds if it's traveling 30 meters per second. But clearly, there's more to physics than Newtonian physics. There is something else going on here. And there's more to light than this wave theory. Light, you know, we saw evidence it behaves like a wave, but man, it is not behaving like a wave, not wave-like in this situation. Well, given that we need a new theory, how about we have no other scientist less than Einstein giving us an explanation or an alternative view of reality here. So if we're going to turn physics on its ear, let's let Einstein do it. And so Einstein kind of was a radical enough thinker to say, let's not stick or remain grounded in this idea of light as some sort of traditional wave. I mean, the whole idea of light as a wave was a bit of a placeholder anyway. People didn't understand what light was, so they started to explore it. And as they explored it, they started to realize, well, light seems to behave like the things that we see around us that we call waves. So let's consider that it might be a wave, but all along we kind of know we can't make a direct observation of that phenomenon of light to say that, yeah, it looks like a wave. I can see crests, I can see troughs. We just see evidence of what a wave behavior demonstrated by light. So Einstein said, let's stop thinking about light as strictly a wave. It's different than anything we really talk about in physics. So he proposed we call it a photon. And here's Einstein's photon explanation of light. So it really boils down to a few key points. Number one, light is we'll refer to it as a photon, and he said that's a discrete package of energy. So instead of thinking it as this wave that carries energy throughout each point on the wave, here's my picture of a wave with its energy stored throughout the wave. Einstein said, don't think of it that way. Think of it as a bundle of energy. Now, it's not that it's not behaving like a wave under certain conditions, so I'll use a little wave symbol here, but it is definitely a package. So it's not like one part of light blends with the other one as a continuous wave. It's like there is a bunch of little things that make up light, he called photons. The energy of a single photon is quantized and can be calculated using a formula, E is equal to HF. So you can see where the energy of the photon is related to the frequency. Now we can quickly convert that. I'll throw another version of this equation at you. It's H times F or HC over lambda. That's the formula. So energy is related to frequency. It's related inversely to the wavelength. Now, let's clarify this formula, pretty straightforward, but very powerful. The H represents something called Planck's constant. Planck's constant is given, depending on how much precision you want to give it, but to 3 significant digits at least, it is 6.63 times 10 to the power of minus 34 joules per second. Okay, so 6.63 times 10 to the minus 34 joules per second. Or if you want to use a different Planck's constant because you want energy in electron volts, it is given as 4.14 times 10 to the minus 15. That's in electron volts per second. So we have two types or two units that we can talk about energy in. It could be in either joules or electron volts. So Planck's constant has two forms. Next idea that Einstein proposed is that in the photoelectric effect, his explanation kind of said that a single photon then, because it's not a wave, can strike an electron in a metal surface. So we see two animations going on over here. Let's focus our attention on them. So in this one, they show looks like yellow light hitting the surface and nothing's happening. That's because if you calculate the energy using the frequency of yellow light, the energy is not enough to excite one of these electrons and get it off the surface. Einstein said to emit a photoelectron, the photon must have enough energy to free the electron from the surface. And then if you hit it with more energy, then any additional energy is the kinetic energy of the photoelectron. So in the second image down here, you'll see this violet light coming down. Now, the violet light has enough energy not only to free the electrons to the surface, but then they can also have some kinetic energy afterwards. So really, the photon energy on this side, which is related to the frequency, and when it's violet light, it's enough, ends up being the amount of work it took to free the electron to the surface and then give it some kinetic energy. And that is a very elegant explanation, or I should put it this way, it's a theory at this point. Einstein never proved this. He never set up an experiment or anything like that. He just suggested that maybe this is what's going on in this invisible world of what's going on between the light and the electrons in the photoelectric effect. And so this is where we are going to stop with Einstein's proposal, this idea that maybe this is what's going on. Now, it's only a theory at this point until we develop an experiment and prove it. And that'll be our next topic. So, in summary, we're going to move from this really limited model of light as a wave, and we are going to start thinking a little more big picture. Light, we're not going to throw out this idea that it's a wave. It works really good for things like interference pattern equations and things like that. Sure, you can explain interference pattern without talking about light as a wave, but we're also going to suggest that maybe it starts to behave like a particle under certain conditions. So this whole wave particle thing, we're going to call it a photon because that's what Einstein said. And who are we to argue with Einstein? So is light a wave? Is it a particle? Maybe it's best just to say it's a photon, which kind of has wave behavior. It's got particle behavior. The energy of a photon then of light is related to the frequency and the wavelength, HF, HC over lambda. So moving forward with our understanding of the nature of light and electromagnetic radiation, we're going to carry forward these two themes, these two big ideas.